Welcome back to our channel Classfly Community. So today is the lecture 2 and here we will be dealing with the topic of electromagnetic waves. So here the subtopics which we will be doing is first the introduction, then the fundamentals of vector calculus, then some terms related to calculus and different types of integrals. Okay. So first of all is the introduction. So in introduction, electromagnetics is the subject that deals with the theory and application of electric magnetic field. So see, whenever we hear the term electromagnetics, if we divide the term in two parts, what we get? Electro and magnetics. What is electro? In electro there will obviously an electric field, and what is magnetics? There will be a magnetic field. So we have already known about the theory, and now we will deeply know about both of the combinations theories, that is the electromagnetics, as well as we will know the application of each electric as well as the magnetic field. Now, the concept of electromagnetics is of prime importance in almost all fields of engineering. As you all are pursuing engineering, so this concept of electromagnetics is not only basically for the ECE department or for the electrical department, but for all the departments. It is a prime importance given to each of the field of engineering. And moreover, especially in the field of engineering, the electromagnetic communication, which forms the foundation of mobile communication, satellite communication, optical fiber communication, etc. That means the more prime importance are given to all the branches, but specially it is given to the electromagnetic communication, because what happens there, they make a foundation of mobile communication, satellite communication and optical communication or etc. Now in all this application, electric and magnetic field properties are utilized to transfer the information. What does this field's properties do? It is utilized to transfer the information. Example: electricity generator, Xerox machine, printer, cathode ray oscilloscope, ammeter, voltmeter, speakers, hard disk of a computer, electrocardiography, transformers, audio video recording, magnetohydrodynamic generator, steel aircrafts are few more examples. So these are the examples. So from here you can remember 5. So the firstmost and the foremost which you should remember is the audio video recording, which we are now using more in this pandemic. Second, we always use the Xerox machine for any of the notes, and for that output we use the printer. So first you need to remember audio video recording, then Xerox machine, then printer. Then you can come back to your ammeter, voltmeter, speaker and hard disk and many more. Now, a course in electromagnetism deals with electric and magnetic fields, which are vectors. So now this is a course in which we require this electric and magnetic field, right? Magnetic field. So these all are vectors. Now it says that for the purpose of describing the properties of electric and magnetic field, in 1881 J.W. Gibbs and Heaviside developed vector analysis. Now what is vector, you must be thinking. So vector, if you remember that we have studied in 11th and 12th, that a quantity that has both magnitude and direction is known as vector. Okay, but it does not have a position. You need to remember this. So now let's move on and see the next topic, that is the fundamentals of vector calculus. So whenever we talk about vector calculus, they are divided in two main classes. One is scalar, another is vector. So scalar, those physical quantities which possess only magnitude and no direction in space, such as temperature, mass, time, volume, etc. These are known as scalar quantity. See, temperature doesn't have any direction. Mass is what? Mass is the weight, so it will not have dimension. Time doesn't have any particular direction. Volume doesn't have any particular direction. So these only possess magnitude. So these are called scalar. Whereas the vector, those physical quantities which have magnitude and direction both and also obey the parallelogram law of addition of vectors, I hope you remember this, are called vector quantities such as velocity, acceleration, force, field strength. That's why electric field and magnetic field both have a magnitude as well as direction, so they are said to be vectors. Now it says that all the quantities which have magnitude and direction are not vectors. All the quantities are not vectors which have magnitude as well as direction. For instance, think of the electric current has magnitude and direction, yet it is not a vector quantity as it does not obey the parallelogram law of addition. That means it need to have magnitude and direction, but as well as it also need to obey the parallelogram law of addition of vectors. So you must remember this. Now we will move on to again the fundamentals of vector calculus. Now we will know about the scalar product or dot product. So the scalar product of two vectors is defined as the product of the magnitude. So it is the product of the magnitude and the cosine of the smaller angle between them. So see, this is the A vector, this is the B vector. So what happens? So whenever what we do, it is the magnitudes product and the cos theta, that is the theta which will be represented as cos theta, and the opposite will be a vector product, it will be sin theta, and this is known as cross product. How you will remember that it is a scalar product and it is a scalar product or dot product? See, as cos theta says that there is a O in cos theta, so you can remember that cos and dot is similar, so it will be dot product, and the opposite will be the sine product, then sine theta. Okay, so now it says that it can be represented by a dot between the vector, so it is called dot product. So A dot B is equal to AB cos theta. This you all have already done. There is nothing new. This is nothing new. Now let's move on to the vector product, or you can say the cross product. The magnitude of two vectors is defined as the vector having a magnitude equal to the product of the magnitude of the two vectors and the sine angle, and is in the direction perpendicular to the plane containing the two vectors. So these are the two vectors, and see, this direction is A into B, so this is perpendicular to both of the vectors. So this is A into B, and just the opposite is minus A into B, or you can say B into A. So you can state that A cross B is equal to AB sin theta, or A cross B is equal to magnitude of A and B sin theta n cap. Okay, now we will move on to some terms related to calculus. So first is the delta operation, which we always see in calculus. So del is a vector differential operator represented by the symbol nabla. Okay, so it is a vector differential operator, and it has a symbol which is known as nabla. When applied to a function defined on a one-dimensional domain, it denotes its standard deviation derivative as defined in calculus. That means a function defined on a one-dimensional domain. So whenever this is applied to a one-dimensional domain, it will represent, or it will denote it as a standard derivative of this concept calculus. Whenever it will be applied to a field, that is a function defined on a multi-dimensional domain, del may denote the gradient, locally steepest slope of a scalar field, or sometimes of a vector field, as in the Navier-Stokes equation. The divergence of a vector field or the curl depending on the way it is applied. So you just need to remember that when it is applied on a one dimensional, it will denote as the standard derivative, and when applied to a field, it will be denoted the gradient of a scalar field, or the divergence of a scalar field, or the curl of a vector field, depending on the way how it will be applied. Now we will see what is gradient. So gradient operation is performed to find the spatial variation of a scalar quantity such as temperature, height, etc. See this symbol, this will be this one, okay. The symbol is wrong here. So please make the changes here. Gradient operation is performed to find the spatial variation of a scalar quantity such as temperature. So the gradient symbol is just the inverse of this delta operation. So we do the spatial variation of the scalar quantities. That means scalar quantities mean what? Which have a magnitude but doesn't have any direction. So what we will do, we will differentiate with respect to each of the three dimensions. That is, one will be dx, delta x, one will be delta y, one will be delta z, and its cap of ax, cap of yx, and cap of zx. So the gradient operation on a scalar field is a vector. For example, electric field is expressed as gradient of potential. Okay, so electric field is expressed as a gradient of potential, and gradient vector, before that, electric field when is expressed as a gradient of potential, see this is an electric field, so this is the gradient, right? So it says that, see this, there was T, so as it is the potential which is V, it have a magnitude but doesn't have a direction. What it does, as it is there is minus, so there will be a minus. Now what we will do, we will do a three dimensional, so delta x, delta y, delta z, and whatever with respect to whatever is happening you will write above. And as the dimension is there, each of the dimension, there will be a cap also there. That means unit vector of each will be there. So there will be a cap x, a cap y, and a cap z. So like this we can represent electric field is expressed as gradient of potential. Last point which you need to remember about this gradient is that gradient vector always point in a direction showing a maximum change of the scalar function. That means whenever the gradient, you need to remember that the gradient vector always point to a direction which will show maximum change of the scalar function. So wherever there will be a maximum change in the scalar function, at that point the gradient vector will direct. So see, like dt is equal to, this is gradient t dot dl. So this is the vector of gradient t, and this is the vector of dl and cos theta. That is product, this is a dot product, so that's why here it is cos theta. Okay, now we will move on to the next part, that is divergence. So this operation is used to evaluate the amount of physical quantity emerging from a small volume. That means there is something in a very small volume, we need to evaluate that how much the amount of physical quantity is emerging from that small volume. So from the definition of the divergence we construct, see, one basic thing you will be thinking that how the symbol of divergence is this gradient, right? So divergence symbol is what? It is gradients plus a dot. So what we will do, as it is here a, similar to gradient, we will have a dimensions 3, a delta x, delta y, delta z, but there will be no unit vector of each. Instead what we will do, there will be a delta ax, delta ay, delta az above. Here we observe that the divergence of vector function is itself a scalar. That means whatever the divergence of a vector function will be, so it will itself be a scalar. The divergence is a measure of how much the vector spreads out from the point in question. So it will measure how much the vector got spread out. For example, we will say positive charge is a source of divergence, but a negative charge is a source of negative divergence. So the tip of a fountain head is a source of positive divergence. So these are the example of divergence, and the symbol of divergence is gradient and a dot. Now curl. In vector calculus, the curl is the vector operation. So what is a curl? So in vector calculus, curl is a vector operator that describes the infinitesimal rotation of a vector field in a three-dimensional Euclidean space. So it will describe the infinitesimal rotation of a vector field. At every point in the field, the curl of that point is represented by a vector. The attributes of this vector, that is length and the direction, characterize the rotation at that point. And the direction of the curl is the axis of rotation as determined by the right hand rule, and the magnitude of the curl is the magnitude of rotation. So here there is a 3 point. In this 3 point you need to remember three things. That curl describes the infinitesimal rotation of a vector field, and in a three-dimensional Euclidean space. Second point, you need to remember that every point of the field, the curl of that point is represented by a vector. And the third point is that the direction of the curl will be the axis of rotation, which we found by the right hand rule, and the magnitude of the curl will be the magnitude of rotation. And the last point which you need to know is that if the vector field represents the flow velocity of a moving field, then the curl is the circulation density of the field. A vector field whose curl is 0 is called irrotational. So here you need to know that a vector field whose curl is 0 is called irrotational, and the curl is a form of differentiation for vector fields. So these are the some terms which is related to calculus. Now we will move on and see how the curl of a vector field F denoted by curl F, or this is gradient. Okay, this is not V, this is gradient into F, or rot F at a point is defined in terms of its projection onto various lines through the point. So you need to see that this gradient into this F will give you, see there is I, J and K cap, K vectors, all are vectors, I, J and K. There will be three things. One will be, in the last line it will be Fx, Fy, Fz, and here it in the second position it will be delta by delta x, delta by delta y, and delta by delta z. And I, J, K are the unit vectors here, that is x, y and z axes respectively. Okay, and see, a gradient into F is F composed of Fx, Fy and Fz. So it shows that the projection of the curl of F onto is defined to be the limiting value of a closed line integral in a plane orthogonal. Okay, so now what is the significance? So curl measures the tendency for the vector field to swirl around, that means to move around. The curl measures this tendency. Dot product checks the parallelness, and the cross products checks the perpendicularity. Okay, so here are terms related to calculation, and now we will see the different types of integrals. So there are three types of integral. First is line integral, then is surface integral, then is volume integral. Now let's extend the concept of integration. So what is line integral? By line we means a path along a curve and a space. So what we are doing here, in a given field vector A and a curve dl, so there is a curve that is L and a field vector which is A. So this will be a line vector which is integrating with L. So it moves from A to B, which is the path, and as it is the dot product, it will be magnitude of A cos theta dl as a line integral of A around L. Okay, so this was the line integral. Now we will see the surface integral and the volume integral. Give a vector field A continuous in a region containing the smooth surface S. We define the surface integral or the flux A through S. So the surface integral thing, the psi is equal to this integration of surface, that is S. So it is as the surface, so it is ds here, and it will be the dot product. So as it is here the magnitude of A cos theta, so A dot an ds, this will be a surface integral. And the volume integral is the closed surface, defines a volume for which we define the integral. So that means here we will define the integral but as a volume, and here this P is the scalar over this volume V. So this is, so wherever the integration is happening, L, line, surface or volume, so if it was line integral then it will be L, if it is surface integral then it will be S, and if it is volume then it will be V. So here as the volume integral of scale P over the volume V we are doing. So these are the three integrals we are completed. So if you have any queries, please comment us down below. We will look over to it, and thank you for watching.
Wow, that's impressive! You have completed a magic today. For more videos, subscribe. Join our Facebook group and Instagram page for group discussion and live magazine videos for exam preparation in an hour. We start at Classfly community for students to learn from a friend in a simple way and support them in their own languages. If you are willing to be that one friend who saves us at the exam night preparation, then please join us by visiting classfly.in.